In the constellation Bootes, where shepherds once saw their eternal guardian among the stars, something stirs in the vast darkness between suns. It moves with the patience of geological time. This wanderer that has known no planetary warmth for longer than complex life has existed on Earth. The object designated 3I Atlas carries within its frozen heart the memory of stellar death and birth. A 4 billion-year journey compressed into a nucleus no larger than a mountain peak lost in cosmic night, beyond Neptune's orbit, where sunlight arrives as the faintest whisper of warmth. This interstellar visitor begins its slow awakening. The distance here measures 43 astronomical units from our Sun, 43 times the span between Earth and the solar fire that drives our seasons. At such remove, solar radiation carries barely enough energy to raise surface temperatures by degrees so small they would escape notice on any world that knows weather. Yet, even this gossamer touch of stellar heat begins to work its patient alchemy on ices that have slept since before the first complex cells learned to breathe oxygen. The comet's surface presents a landscape darker than fresh asphalt, absorbing every photon that reaches it across the emptiness. Beneath this thermal blanket, ancient frozen volatiles respond to temperature changes measured in fractions of Kelvin. Water molecules that crystallized when the Milky Way itself wore a different spiral pattern start their reluctant transformation from solid to vapor, releasing gases that have waited geological ages for this moment of liberation. Only took 4 billion years of wandering to find a star. Only needed to cross the gravitational boundary of a solar system it had never encountered. Only required the kind of patience that makes continental drift seem hurried. The irony settles like cosmic dust. This visitor carries more time in its frozen nucleus than entire species have existed on Earth. Yet it will spend mere months in our solar system's embrace before continuing its eternal journey into darkness. Scientists on Earth measure its approach with radio telescopes sensitive enough to detect the electromagnetic whisper of sublimating gases millions of kilometers away. The Atacama Desert arrays point their aluminum faces toward this approaching messenger, gathering data streams that reveal molecular signatures unlike anything born in our local stellar neighborhood. Each spectrum line tells of chemical processes that occurred in regions of space where stellar formation follows different rhythms, where the very elements cooled and condensed under alien gravitational influences. The visitor's hyperbolic trajectory speaks of origins beyond our Sun's gravitational reach. Its orbital mechanics describe a path that began in interstellar space and will end in interstellar space, a mathematical arc that intersects our solar system for what amounts to an astronomical moment. Ground-based observatories in Chile, Hawaii, and the Canary Islands coordinate their observations with the methodical precision of astronomers who understand that cosmic visitors follow schedules measured in millions of years. Deep in the comet's nucleus, beneath layers of organic compounds darker than coal tar, water ice begins its phase transition. The process unfolds with geological slowness, molecules breaking their crystalline bonds one by one, forming vapor that seeps through porous rock matrix toward the surface. This outgassing creates the faintest suggestion of atmosphere around the visitor, a tenuous envelope of gases that extends perhaps a few hundred kilometers into space before dispersing into the solar wind. What makes this awakening remarkable lies not in its visible drama, which remains minimal at such distance, but in its chemical signature. Spectroscopic analysis reveals isotope ratios that differ subtly from solar system norms, suggesting formation in stellar environments where different nuclear processes dominated. The deuterium to hydrogen ratio carries information about the temperature and density of the molecular cloud where this wanderer first condensed from cosmic gas. These measurements require instruments capable of detecting differences in atomic mass so slight they would be meaningless in any earthly context. The mystery deepens with each observation. Traditional models of interstellar object behavior predict certain patterns of outgassing and surface evolution as these visitors approach our Sun. Yet, 3I Atlas displays irregularities that challenge current understanding of how ancient ices respond to solar radiation. Some wavelengths of infrared light reveal more water vapor than expected. Others suggest the presence of exotic frozen compounds that should not exist in stable form across interstellar distances. Observatory networks from Mauna Kea to the European Southern Observatory maintain continuous surveillance, their CCD cameras recording minute changes in brightness and spectral composition. Each image captures light that traveled across the solar system to reveal the chemical nature of matter that formed before Earth's accretion disk had settled into planetary orbits. The photons arriving at terrestrial telescopes carry information encoded in wavelengths that speak of stellar nucleosynthesis processes in regions of the galaxy our species will never visit. As autumn deepens across Earth's northern hemisphere, this interstellar messenger continues its approach with the inevitability of celestial mechanics. Its path remains predictable to within meters across distances measured in billions of kilometers. Yet, the physical processes occurring on its surface continue to confound models built from observations of local comets. Like a word spoken in a foreign language that shares familiar sounds but conveys meanings we cannot quite grasp. 3I Atlas carries messages from stellar environments that operated according to physics we understand, but chemistry we are still learning to decode. The nucleus of 3I Atlas holds within its frozen matrix the compressed history of a stellar nursery that flickered to life and death before our Sun ignited its first hydrogen fusion. 4 billion years ago, when Earth existed only as scattered planetesimals orbiting through clouds of primordial dust. This wanderer began its formation in a molecular cloud so distant that light from our nascent solar system had not yet reached its boundaries. The chemical signatures locked in its ancient ices tell of nucleosynthesis processes that operated under conditions fundamentally different from those that forged the rocky planets we call home. In the outer regions of a spiral arm now rotated beyond our current galactic position, temperatures dropped below the sublimation point of water, a carbon dioxide, and more exotic compounds. The molecular cloud that birthed this visitor contained ratios of heavy elements that speak of multiple generations of stellar death and rebirth. Supernovae had enriched this region with calcium, magnesium, and iron in proportions that differ measurably from solar system abundances. These elemental fingerprints remain preserved in the comet's nucleus like geological strata, recording conditions in a stellar formation region that operated according to its own gravitational and chemical rhythms. Infrared spectroscopy reveals the presence of crystalline water ice within the nucleus, a discovery that challenges models of interstellar thermal evolution. Crystalline ice forms only under specific temperature and pressure conditions, requiring either rapid cooling from liquid phase or sustained heating that allows molecular reorganization. Neither process should occur naturally during the gradual condensation expected in cold molecular clouds. Yet here, the evidence persists in wavelengths of absorbed infrared radiation that correspond precisely to crystalline H2O lattice structures. Only took 1 billion years of interstellar radiation to maintain crystal structure. Only needed cosmic ray bombardment intense enough to sterilize planets to preserve molecular arrangements. Only required temperatures approaching absolute zero to keep water molecules locked in formations that would melt instantly in Earth's atmosphere. The paradox settles into the comfortable realm of cosmic ironies, where the coldest environments in the galaxy preserve the most organized forms of matter. The deuterium to hydrogen ratio in the comet's water vapor measures 1.6 times the terrestrial ocean value, indicating formation in regions where stellar nucleosynthesis followed different pathways. This isotopic signature suggests that the molecular cloud experienced enrichment from massive stars, whose fusion processes produced heavy hydrogen in greater abundance than the stellar population that influenced our local stellar neighborhood. Each deuterium atom represents nuclear reactions that occurred in stellar cores massive enough to synthesize elements beyond iron before collapsing into neutron stars or black holes. Deep space monitoring stations detect subtle variations in the radio emissions from the comet's developing coma. These electromagnetic signatures correspond to rotational transitions in molecules like hydrogen cyanide, formaldehyde, and carbon monoxide compounds that formed through surface chemistry processes operating at temperatures where chemical reaction rates drop to nearly zero. The presence of these complex organics indicates that even in the near vacuum of interstellar space, given sufficient time, simple molecules can combine into more elaborate structures through quantum tunneling effects and cosmic ray-induced reactions. The orbital mechanics of 3I Atlas reveal additional mysteries about its origins. Its trajectory, when traced backward through galactic coordinates, suggests passage through regions of space where stellar density exceeds local galactic averages. This journey would have exposed the comet to gravitational perturbations from multiple star systems, yet its nucleus shows no evidence of the repeated thermal cycling that such encounters should produce. The surface composition remains remarkably homogeneous, as if the wanderer somehow avoided the tidal stresses and radiative heating that should accompany close stellar passages. Astronomical calculations indicate that maintaining such chemical preservation across billions of years requires a combination of circumstances so specific that current models struggle to explain their persistence. The comet needed to avoid regions of space where interstellar medium density would cause significant erosion through particle bombardment. It required trajectory adjustments precise enough to navigate gravitational fields without experiencing tidal disruption. Most improbably, it needed protection from galactic cosmic rays intense enough to alter molecular structure through radiation damage. Ground-based spectrometers continue to detect unexpected absorption lines in the comet's developing atmosphere. Wavelengths corresponding to sulfur-bearing compounds appear stronger than models predict for objects formed in low metallicity environments. The sulfur isotope ratios suggest nucleosynthesis in stellar environments where neutron capture processes operated under conditions not found in current star-forming regions of our galactic neighborhood. These signatures persist despite 4 billion years of cosmic ray exposure that should have altered surface chemistry beyond recognition. As 3I Atlas continues its approach, each night of observation adds new details to its chemical biography. The story emerges slowly, written in isotope ratios and molecular abundances that speak of stellar formation processes operating under physical conditions that no longer exist in the galaxy's current evolutionary phase. Like archaeological artifacts from civilizations that developed technologies we have forgotten how to reproduce. This interstellar visitor carries information about cosmic chemistry from an era when the Milky Way itself followed different patterns of stellar birth and death. The mystery deepens with recognition that this ancient wanderer represents not an anomaly, but a messenger from galactic epochs that operated according to nucleosynthesis processes we can calculate but have never directly observed. Its frozen nucleus holds samples of matter that condensed from stellar winds enriched by supernovae whose light faded before complex life learned to harness chemical energy on Earth. Only took half the current age of the universe to deliver this sample to instruments capable of reading its molecular text. Only needed the precise gravitational choreography of galactic rotation to bring these ancient ices within range of terrestrial spectroscopes. Only required the kind of cosmic patience that transforms stellar death into chemical legacy, preserved in frozen archives that wander between the stars until gravity guides them home. The mathematics of 3I Atlas's hyperbolic trajectory unfold with the elegant precision of celestial mechanics, each calculation revealing the gravitational choreography that guided this ancient wanderer from interstellar space into our solar system's embrace. Its orbital eccentricity measures 1.93, a value that speaks of origins beyond our sun's gravitational influence and destination in the cosmic darkness beyond Pluto's realm. This hyperbolic path describes a mathematical curve that intersects our planetary neighborhood for mere months before continuing its eternal journey through the galaxy's spiral arms. Astronomers trace the visitor's approach vector backward through space and time, following gravitational breadcrumbs that reveal its passage through stellar neighborhoods our species has never observed. The calculations require accounting for the sun's motion through the local stellar medium, the gravitational influence of nearby star systems, and the subtle perturbations caused by our galaxy's rotation around its supermassive black hole. Each variable in these equations represents forces that operated across distances and timescales that dwarf human comprehension. Yet their combined influence guided this frozen messenger to arrive at our coordinates with clockwork precision. The comet's velocity at solar system entry measured 26.33 kilometers per second relative to our sun's rest frame, a speed that speaks of acceleration through gravitational fields spanning parsecs of interstellar space. This velocity vector, when decomposed into galactic coordinates, suggests that 3Y Atlas originated from a region of space currently located in the direction of the constellation Lynx, though its actual birth occurred when that stellar neighborhood occupied entirely different galactic coordinates. The Wanderer has traveled roughly 1/6 of the way around the galaxy's circumference during its 4 billion-year journey. Orbital mechanics calculations reveal that the visitor's closest approach to our Sun will occur at a distance of 1.09 astronomical units, placing it just beyond Earth's orbit during late autumn. At this perihelion point, gravitational acceleration will increase the comet's velocity to 54.7 kilometers per second, sufficient to escape our solar system entirely and return to interstellar space. The precision of these calculations depends on measurements accurate to within meters across distances spanning billions of kilometers, a testament to the mathematical tools that allow humans to predict cosmic events with extraordinary accuracy. Only took 43,000 years to cross from interstellar space to Neptune's orbit. Only needed gravitational focusing by our Sun to compress 4 billion years of wandering into a few months of observable approach. Only required the kind of mathematical precision that makes planetary motion predictable to the minute across millennia. The irony rests in numbers. This visitor follows trajectories calculable with extraordinary accuracy. Yet the forces that originally set it in motion operated in stellar environments we can model but never directly observe. The comet's trajectory intersects our solar system at an angle of 38, 7 degrees relative to the ecliptic plane, indicating that its original stellar neighborhood possessed different orbital characteristics than our current galactic position. This inclination suggests formation in a region where stellar velocities followed patterns distinct from the orderly rotation found in our spiral arm. The gravitational signatures preserved in this orbital geometry speak of passage through stellar associations where massive stars influence local space-time curvature in ways that shape the trajectories of everything within their gravitational reach. Deep space tracking networks monitor the visitor's position with radio interferometry techniques that achieve positional accuracy measured in thousandths of an arcsecond. These measurements require synchronization between telescopes separated by continental distances, creating virtual apertures capable of resolving details smaller than atomic nuclei across interplanetary distances. The data streams flowing from these observations contain enough information to detect gravitational perturbations caused by asteroids too small to observe directly, revealing the invisible architecture of gravitational influence that guides celestial mechanics. The mystery embedded in 3I Atlas's trajectory lies not in its mathematical predictability, but in the improbable sequence of gravitational encounters that preserved its structural integrity across galactic distances. Computer simulations indicate that maintaining coherent nucleus composition while navigating the gravitational chaos of stellar formation regions requires avoidance of close encounters with massive objects that should occur statistically once every few million years. Yet, this wanderer survived 40 centuries of such statistical hazards while preserving chemical signatures that speak of its pristine interstellar origins. Gravitational modeling reveals additional complexities in the comet's past trajectory. The orbital elements, when propagated backward through galactic coordinates, indicate passage through the gravitational influence of at least 17 different stellar systems during the past billion years. Each encounter should have produced measurable changes in orbital characteristics, yet the current trajectory shows no evidence of the chaotic perturbations that such gravitational interactions typically generate. The mathematics suggest either extraordinary luck or gravitational shielding mechanisms that current astrophysical models struggle to explain. As 3I Atlas continues its approach, each positional measurement refines the orbital solution with increasing precision. The trajectory calculations now achieve accuracy sufficient to predict the comet's location years into the future. Even as it travels beyond the influence of our solar system's gravity, these mathematical projections reveal that the visitor will require approximately 67,000 years to reach the distance where our sun's gravitational influence becomes negligible compared to that of neighboring stars. The orbital dynamics also predict subtle changes in the comet's rotation state as it approaches perihelion. Tidal forces from our sun's gravity will gradually alter the nucleus's tumbling motion, synchronizing its rotation period with specific orbital resonances. These rotational changes will modify the pattern of outgassing from the comet's surface, creating asymmetric thrust vectors that will slightly adjust its trajectory in ways too small to measure directly, but large enough to accumulate over interstellar distances. Ground-based observatories continue tracking the visitor's progress with the methodical precision of astronomers who understand that cosmic mechanics operate according to mathematical principles that remain constant across galactic distances and geological time. Each measurement adds another data point to orbital solutions that describe motion governed by the same gravitational laws that shape planetary orbits, yet operating on scales where individual trajectories span the lifetime of stellar populations. Only needed Newton's inverse square law to describe motion across galactic distances. Only required Einstein's corrections to account for gravitational effects in the curved space-time near massive objects. Only demanded the kind of mathematical elegance that makes universal physical laws applicable from laboratory scales to cosmic distances, revealing that this ancient wanderer follows the same gravitational choreography that guides planets around stars and stars around galactic centers, connected through equations that speak the universal language of celestial mechanics. Solar radiation begins its patient work on the ancient surface of 3I Atlas as the wanderer crosses the invisible boundary where our sun's energy flux exceeds the faint background warmth of interstellar space. At 38 astronomical units from our star, photons arrive with intensity barely sufficient to raise surface temperatures above the 2.7 Kelvin baseline of cosmic microwave background radiation. Yet even this gossamer touch of stellar heat triggers molecular processes that have waited 4 billion years for activation, as water molecules locked in crystalline matrices begin their reluctant transition from solid to vapor phase. The sublimation process unfolds with geological patience, governed by thermodynamic principles that operate at temperatures where molecular motion nearly ceases. Surface regions facing our sun experience temperature increases measured in tens of Kelvin, sufficient to break the hydrogen bonds that maintain ice crystal structure in the comet's outer layers. These liberated water molecules, along with carbon dioxide, carbon monoxide, and more exotic frozen compounds, seep through the porous matrix of the nucleus toward regions of lower pressure, eventually escaping into space to form the tenuous atmosphere that astronomers call a coma. Infrared imaging reveals asymmetric heating patterns across the comet's surface, as its irregular shape creates zones of varying solar illumination. The nucleus rotates with a period of 7.3 hours, causing different surface regions to experience cyclical heating and cooling that drives complex outgassing dynamics. Areas that receive direct sunlight for extended periods develop active sublimation zones, while regions in permanent shadow remain locked in the thermal conditions of interstellar space. This temperature contrast creates internal pressure gradients that influence how gases migrate through the nucleus's porous interior. Only took 38 astronomical units of approach to begin awakening processes dormant since stellar formation. Only needed solar flux intensity equivalent to moonlight on Earth to trigger phase transitions in ices that survived galactic cosmic ray bombardment. Only required thermodynamic conditions barely above absolute zero to begin the slow alchemy that transforms a dark, silent wanderer into something visible to human instruments. The gentle irony settles like cosmic dust. This visitor responds to our sun's distant warmth with chemical processes that unfold more slowly than continental drift, yet follow the same physical laws that govern boiling water. Spectroscopic analysis of the developing coma reveals molecular signatures that challenge current models of cometary outgassing. The water vapor production rate increases non-linearly with solar distance, suggesting internal heating mechanisms beyond simple surface sublimation. Subsurface ice deposits, insulated by layers of organic compounds darker than charcoal, may be experiencing thermal wave propagation that reaches depths of several meters below the surface. This delayed heating creates outgassing patterns that persist even when surface regions rotate into shadow, maintaining atmospheric production through thermal energy stored in the nucleus's interior. The composition of gases escaping from 3I Atlas differs subtly from that observed in solar system comets. Deuterium-enriched water vapor appears in ratios that speak of formation in molecular clouds, where stellar nucleosynthesis followed different pathways than those that influenced our local stellar neighborhood. Carbon monoxide molecules show isotopic signatures, suggesting synthesis in environments where neutron capture processes operated under conditions no longer found in our galaxy's current star-forming regions. Each molecular species carries chemical fingerprints that reveal details about stellar evolution processes from galactic epochs we can calculate but never directly observe. Radio telescopes detect the characteristic emission lines of hydroxyl radicals, fragments of water molecules dissociated by solar ultraviolet radiation in the comet's outer atmosphere. These OH molecules absorb and re-emit specific wavelengths of radio energy, creating signals detectable from Earth despite the enormous distances involved. The intensity and distribution of hydroxyl emission provides indirect measurements of water vapor production rates, allowing astronomers to monitor the comet's activity level as it responds to increasing solar heating during its approach. The mystery deepens with observations of unusual dust production patterns accompanying the gas outflow. Traditional cometary models predict that sublimating ices should entrain dust particles from the nucleus surface, creating the visible tails that make comets spectacular to observe. Yet, 3I Atlas shows remarkably low dust-to-gas ratios, suggesting that its surface composition differs significantly from objects formed in our solar system's protoplanetary disk. The nucleus appears to be releasing primarily gaseous materials, while retaining most of its solid particulate matter, a behavior that challenges understanding of how sublimation processes affect cometary surface structure. Ground-based spectrometers continue monitoring the evolving chemical signature of the comet's atmosphere as outgassing rates increase with proximity to our Sun. Each spectrum reveals new molecular species liberated from ice matrices that preserve them across interstellar distances. Formaldehyde, hydrogen sulfide, and complex organic compounds appear in abundances that speak of chemical processes operating in the comet's subsurface layers, where catalytic reactions may occur on mineral grain surfaces exposed to migrating gases. Deep space infrared observatories track thermal emission from the comet's nucleus, measuring surface temperatures that rise with mathematical precision as solar heating overcomes the radiative cooling that maintained thermal equilibrium during the wanderer's interstellar journey. These temperature measurements, combined with models of internal heat conduction, suggest that thermal waves penetrate several meters into the nucleus, activating sublimation processes in subsurface ice deposits that have remained frozen since the comet's formation 4 billion years ago. As autumn deepens across Earth's northern hemisphere, 3I Atlas continues its patient response to our Sun's increasing influence. The outgassing patterns follow thermodynamic principles that operate with the same reliability across interstellar distances as they do in terrestrial laboratories. Yet, the chemical products emerging from this ancient nucleus carry molecular signatures from stellar environments that operated according to nucleosynthesis, processes our species has never witnessed. Only needed the universal constancy of physical laws to make this ancient chemistry readable by modern instruments. Only required the patient interaction of solar energy with matter that preserves 4 billion-year-old samples of galactic chemical evolution. Only demanded the kind of scientific precision that allows humans to decode molecular messages from stellar nurseries that flickered to life and death before complex life learned to harness photosynthesis, revealing that the basic processes of phase transition and molecular dissociation operate with identical principles across cosmic distances and geological time, connecting this wanderer's awakening to the same thermodynamic laws that govern every transformation from solid to gas, from frozen silence to gaseous whisper, from interstellar preservation to solar system revelation. Light filtered through the tenuous atmosphere of 3I Atlas carries within its wavelength signatures the chemical biography of stellar environments that operated under conditions fundamentally different from those found in our current galactic neighborhood. Each photon absorbed and re-emitted by molecules in the comet's developing coma provides spectroscopic evidence of nucleosynthesis processes that occurred in massive stars whose fusion reactions followed pathways no longer active in the Milky Way's present evolutionary phase. The atomic transitions recorded in these spectra speak of elemental abundances forged in supernova explosions that enrich the molecular cloud where this wanderer first condensed from cosmic gas and dust. Spectrometers operating across the electromagnetic spectrum reveal isotopic ratios that challenge models of galactic chemical evolution. The nitrogen-15 to nitrogen-14 ratio in hydrogen cyanide molecules exceeds solar system values by factors that indicate formation in regions where stellar mass functions favored the production of elements through neutron capture processes. These isotopic signatures preserve information about the stellar population that influenced the chemistry of the comet's birth environment, where massive stars synthesized heavy elements through nuclear reactions operating at temperatures and pressures that dwarf those found in our Sun's core. Infrared absorption lines corresponding to carbon dioxide show unusual isotopic distributions that speak of synthesis in stellar atmospheres where convective mixing transported nuclear reaction products from deep interior zones to photospheric layers. The carbon-13 enrichment observed in these molecules suggests exposure to stellar winds from asymptotic giant branch stars, whose helium-burning shells produced isotope ratios through the slow neutron capture process. Such chemical signatures indicate that the molecular cloud environment contained contributions from stellar populations with different mass distributions than those currently active in our spiral arm. Only took 4 billion years of preservation in interstellar space to maintain isotopic signatures from stellar nucleosynthesis. Only needed temperatures approaching absolute zero to prevent thermal equilibration that would erase chemical fingerprints from extinct stellar environments. Only required the patient accumulation of spectroscopic data to decode molecular messages written in wavelengths of absorbed light. The cosmic irony settles gently. This ancient chemistry remains readable because it avoided the thermal and chemical processing that would occur during planetary formation, preserving pristine samples of galactic evolution in frozen archives that wander between the stars. Ultraviolet spectroscopy reveals the presence of complex organic molecules that form through surface chemistry processes, operating in the near-vacuum conditions of interstellar space. Polycyclic aromatic hydrocarbons appear in the comet's outer atmosphere as sublimating ices release compounds that condensed on grain surfaces through reactions driven by cosmic ray interactions and ultraviolet radiation from distant stars. These molecular species represent chemical evolution that occurred over timescales measured in hundreds of millions of years, as simple carbon-bearing molecules gradually assembled into more complex structures through quantum tunneling effects and radiation-induced bond formation. The deuterium chemistry of 3I Atlas provides particularly striking evidence of its exotic origins. Water molecules enriched in heavy hydrogen by factors of 3 relative to terrestrial oceans indicate formation in molecular cloud environments where temperature and density conditions favored the incorporation of deuterium into ice crystal lattices. This isotopic enhancement occurs only in regions of space where stellar heating remains insufficient to drive the chemical reactions that typically deplete deuterium through exchange processes with normal hydrogen. The preservation of such extreme isotopic ratios requires thermal isolation that has persisted across galactic distances and geological time. Radio observations detect emission lines from methanol, formaldehyde, and other organic species that reveal details about grain surface chemistry in the comet's formation environment. These molecules form through catalytic processes that operate on silicate and carbonaceous dust grains exposed to hydrogen atoms and simple carbon compounds in the diffuse interstellar medium. The relative abundances of different organic species provide constraints on the physical conditions that existed in the molecular cloud, including temperature, density, and radiation field intensity during the epochs when this chemistry operated most efficiently. The mystery embedded in these spectroscopic signatures lies in their remarkable preservation across the chaotic gravitational environments that characterize stellar formation regions. Computer models indicate that maintaining such chemical integrity while traversing multiple stellar neighborhoods requires avoidance of heating events that should occur statistically during passage through regions of enhanced stellar density. Yet the molecular evidence suggests that 3I Atlas preserved its original isotopic and chemical signatures despite encountering gravitational perturbations from dozens of stellar systems during its galactic journey. Ground-based observatories continue accumulating spectroscopic data as the comet's outgassing rate increases with solar proximity. Each night of observation adds new molecular detections to the growing catalog of chemical species emerging from the nucleus. Hydrogen sulfide, ammonia, and exotic sulfur-bearing compounds appear with abundances that speak of formation in stellar environments where sulfur chemistry operated under reducing conditions not found in oxidizing planetary atmospheres. The sulfur isotope ratios indicate nucleosynthesis in stellar cores, where neutron flux densities exceeded those found in current stellar populations. Deep space infrared telescopes monitor thermal emission from dust grains entrained in the comet's gas outflow, revealing mineral compositions that differ from those found in asteroidal and planetary materials. The silicate absorption features show crystalline structures that indicate formation at temperatures exceeding those expected in cold molecular clouds, suggesting either heating events during the comet's interstellar journey or inheritance of processed materials from stellar environments where grain annealing occurred in stellar winds or circumstellar disks. As 3I Atlas continues its approach toward perihelion, the spectroscopic evidence accumulates into a chemical portrait of galactic evolution from epochs when stellar formation followed different patterns than those observed in current star-forming regions. The molecular signatures emerging from this ancient nucleus read like a periodic table written in isotope ratios and elemental abundances that speak of nucleosynthesis processes operating under physical conditions that no longer exist in our galaxy's present evolutionary phase. Only needed the universal constancy of atomic physics to make these ancient chemical signatures readable by modern spectrometers. Only required the precise wavelength calibration of laboratory measurements to decode molecular transitions that preserve information about stellar environments from galactic epochs we can model but never directly observe. Only demanded the kind of scientific patience that allows astronomers to read cosmic history written in the language of quantum mechanics, where each absorbed photon carries information encoded in atomic energy levels that remain constant across cosmic distances and geological time, revealing that this wanderer's chemistry speaks of stellar death and birth from eras when the galaxy itself operated according to different patterns of element synthesis and distribution. Thousands of smaller fragments drift in the gravitational wake of 3I Atlas, invisible to all but the most sensitive instruments, yet detectable through their collective influence on the comet's observable properties. These companions range in size from boulders several meters across to dust grains smaller than bacteria, each carrying the same ancient chemistry that characterizes their parent nucleus. The debris field extends across millions of cubic kilometers of space, distributed along the comet's orbital path according to the complex dynamics of gravitational attraction, solar radiation pressure, and the subtle thrust generated by asymmetric outgassing from the primary nucleus. Radio interferometry networks detect the electromagnetic signatures of this invisible swarm through careful analysis of signal variations as the primary comet moves across the sky. The minute fluctuations in received signal strength reveal the presence of objects too small and dark to observe directly, yet massive enough to create detectable gravitational microlensing effects when they pass between Earth-based telescopes and distant radio sources. These observations require synchronization between facilities separated by continental distances, creating virtual apertures capable of resolving gravitational influences smaller than those produced by individual asteroids in our outer solar system. Infrared surveys reveal thermal emission from the largest fragments in the debris field, objects that absorb solar radiation and re-radiate energy at wavelengths characteristic of surfaces heated to temperatures barely above those of interstellar space. The thermal signatures indicate compositions remarkably similar to the primary nucleus surfaces, darker than charcoal. Overlying subsurface ice deposits that respond to solar heating with the same patient sublimation processes observed in the main comet. These larger companions appear to be genuine fragments rather than captured interstellar debris, suggesting that 3I Atlas experienced fragmentation events during its 4 billion-year journey through galactic space. Only took gravitational perturbations measured in micrometers per second, squared to separate these fragments from their parent nucleus. Only needed thermal cycling across temperature ranges spanning tens of Kelvin to create internal stresses sufficient to fracture ancient ice matrices. Only required the kind of patient mechanical weathering that operates on timescales longer than biological evolution to sculpt this wandering family from a single primordial object. The quiet irony emerges in numbers. Forces barely detectable by human instruments shape this debris field across distances and timescales that dwarf terrestrial geological processes. Spectroscopic analysis of the larger fragments reveals chemical signatures identical to those found in the primary nucleus, confirming their common origin in the molecular cloud environment that existed 4 billion years ago. The deuterium enrichment, exotic isotope ratios, and organic compound abundances appear consistent across all detectable members of the swarm, indicating that fragmentation occurred without significant chemical alteration of the original material. This preservation suggests that separation events involved mechanical fracture rather than thermal processing that would alter the isotopic signatures encoded in ancient ice deposits. The distribution of fragment sizes follows power law scaling relationships that speak of collisional cascades operating over geological timescales. Computer simulations indicate that the current size distribution results from billions of years of micrometeorite impacts, cosmic ray bombardment, and thermal stress cycles that gradually fragmented the original nucleus through processes analogous to those that shape asteroid families in our solar system. The mathematical relationships governing this size distribution reveal details about the mechanical properties of interstellar ice matrices that have never been directly measured in laboratory environments. Orbital mechanics calculations reveal that the debris field maintains coherent motion despite the gravitational chaos encountered during passage through multiple stellar neighborhoods. The fragments follow trajectories that remain gravitationally bound to the primary nucleus across distances comparable to planetary orbital radii. Yet, the binding energies involved measure orders of magnitude smaller than those that hold asteroid families together. This gravitational architecture requires that fragmentation occurred recently enough that tidal disruption from stellar encounters has not yet dispersed the companions into independent interstellar trajectories. The mystery deepens with recognition that maintaining such gravitational coherence across galactic distances requires avoidance of close encounters with massive objects that should occur statistically during any 4 billion-year journey through stellar formation regions. Computer models indicate that preserving debris field integrity while navigating the gravitational influence of multiple star systems requires a combination of orbital characteristics and encounter geometries so specific that their persistence challenges current understanding of interstellar object evolution in galactic gravitational environments. Deep space monitoring networks detect subtle variations in the electromagnetic properties of interplanetary space as the debris field passes through regions populated by charged particles from the solar wind. The interaction between this ancient matter and our Sun's plasma environment creates minute perturbations in magnetic field strength and particle density that propagate as magnetohydrodynamic waves detectable by spacecraft throughout the outer solar system. These signals provide indirect measurements of the total mass and spatial distribution of material in the swarm, revealing details about debris field architecture that remain invisible to optical observations. Gravitational modeling suggests that the largest fragments in the debris field may themselves possess smaller companions, creating hierarchical structure reminiscent of asteroid systems, but operating under gravitational conditions so weak that thermal expansion from solar heating could overcome binding forces. The delicate balance between gravitational attraction and disruptive forces creates dynamical instabilities that may lead to further fragmentation as the swarm approaches perihelion, potentially generating new debris populations that will accompany 3I Atlas during its departure from our solar system. As the interstellar visitors continue their approach, Ground-based observatories maintain surveillance of the debris field with instruments sensitive enough to detect changes in fragment distribution caused by gravitational perturbations from planetary masses. Jupiter's immense gravitational influence will gradually alter the trajectories of smaller debris, potentially scattering some fragments into elongated orbits that could persist in our solar system long after the primary nucleus departs for interstellar space. These calculations require accounting for gravitational effects that operate across astronomical distances with precision sufficient to predict orbital evolution over millions of years. The debris field accompanying 3I Atlas represents more than a collection of ancient ice fragments. It constitutes a gravitational archive of interstellar evolution processes that operated across galactic distances and geological time. Each fragment carries the same chemical signatures that speak of stellar nucleosynthesis from epochs when our galaxy followed different patterns of star formation and element distribution. Only needed the patient accumulation of gravitational perturbations to shape this wandering family from primordial material that preserves samples of cosmic chemistry from stellar environments we will never directly observe. Only required the delicate balance between binding and disruptive forces to maintain debris field coherence across distances that span multiple stellar neighborhoods. Only demanded the kind of gravitational precision that allows thousands of ancient ice fragments to follow coordinated trajectories through space, connected by forces barely stronger than those that hold soap bubbles together, yet persistent enough to survive 4 billion years of galactic wandering, revealing that even the most tenuous gravitational relationships can endure across cosmic distances when undisturbed by the chaotic forces that typically characterize stellar formation regions. Jupiter's immense gravitational field begins its subtle influence on the trajectories of both the primary comet and its accompanying debris as the interstellar visitors cross the invisible boundary where the giant planet's gravitational sphere of influence extends into the realm beyond Saturn's orbit. The gas giant's mass, equivalent to 318 Earths, creates gravitational perturbations that propagate across astronomical distances with mathematical precision, altering orbital elements solved by amounts measured in meters per second, yet accumulating into trajectory changes that will determine the ultimate fate of individual fragments in the ancient swarm. The gravitational mechanics unfold according to the three-body problem that has challenged mathematicians since Newton first formulated the inverse square law of universal attraction. Jupiter's influence operates through tidal forces that differentially accelerate objects based on their position relative to the planet's mass center, creating velocity changes that vary across the debris field according to the inverse cube of distance. These minute accelerations, barely detectable by the most sensitive instruments, accumulate over months of approach to produce orbital modifications that will scatter some fragments toward the inner solar system while deflecting others onto trajectories that lead beyond the heliopause into interstellar space. Computational simulations reveal the complex dynamics governing the interaction between Jupiter's gravity and the loosely bound debris field. The largest fragments, with masses comparable to small asteroids, experience gravitational deflections that modify their velocities by several meters per second during closest approach to the giant planet. These velocity changes, though minute compared to the fragments' orbital speeds, prove sufficient to alter their binding relationships with the primary nucleus, potentially liberating some companions onto independent heliocentric orbits that will persist long after 3I Atlas departs our solar system. Only took gravitational acceleration measuring thousandths of Earth's surface gravity to alter 4 billion-year-old trajectories. Only needed Jupiter's mass concentration to focus perturbations that will determine whether ancient ice fragments remain gravitationally bound or achieve independent orbital status. Only required the patient accumulation of tiny accelerations to reshape debris field architecture through forces that operate with the same mathematical precision across interplanetary distances as they do in laboratory demonstrations of gravitational attraction. The cosmic irony settles like orbital mechanics. This gas giant's influence will determine the future of matter that predates our solar system's formation, applying contemporary gravitational forces to redirect ancient wanderers according to the same physical laws that shaped planetary orbits around our Sun. The gravitational encounter creates resonance effects that modify the rotation states of individual fragments according to their irregular shapes and internal mass distributions. Tidal torques from Jupiter's gravity field induce tumbling motions that alter how solar radiation pressure affects the fragment's trajectories, creating non-gravitational forces that further complicate orbital predictions. These effects operate most strongly on elongated objects whose rotation axes become aligned with Jupiter's gravitational gradient, producing systematic changes in orbital elements that accumulate over the months-long gravitational encounter. Radio tracking networks monitor minute changes in the Doppler signatures of signals reflected from the larger debris fragments, detecting velocity perturbations that reveal the real-time influence of Jovian gravity on objects too small for optical observation. The measurements require frequency stability approaching 1 part in 10 billion, sufficient to detect velocity changes smaller than those produced by gentle terrestrial breezes, yet persistent enough to alter interplanetary trajectories by millions of kilometers over astronomical timescales. These observations provide direct verification of gravitational theory operating under conditions where classical mechanics achieves precision limited only by instrumental sensitivity. The mystery embedded in these gravitational interactions lies in their sensitivity to initial conditions that were established 4 billion years ago in stellar environments we can model but never directly observe. Computer simulations indicate that the current distribution of fragment trajectories depends critically on the original relative velocities established during the debris field's formation, velocities that in turn reflect the mechanical properties of interstellar ice matrices that consolidated under thermal and pressure conditions no longer found in our galaxy's current star-forming regions. Gravitational modeling reveals that Jupiter's influence will preferentially capture fragments with specific orbital characteristics, creating a selection effect that determines which samples of ancient interstellar chemistry will remain accessible to future observation within our solar system. The captured objects will follow elongated orbits that bring them periodically within range of terrestrial instruments, potentially providing ongoing opportunities to study matter that formed in molecular cloud environments from galactic epochs when stellar nucleosynthesis operated under different conditions than those found in contemporary stellar populations. Deep space navigation networks calculate the precise timing of gravitational encounters between Jupiter and individual debris fragments, predictions that require accounting for the gravitational influence of all major planetary masses, as well as relativistic corrections to Newtonian mechanics. These calculations achieve accuracy sufficient to predict closest approach times within minutes across encounters spanning months of orbital evolution, demonstrating the mathematical precision with which gravitational dynamics operate even under the complex multi-body conditions that characterize planetary system environments. The gravitational choreography becomes further complicated by the influence of solar radiation pressure on fragments small enough that photon momentum transfer becomes comparable to gravitational acceleration from distant planetary masses. The Yarkovsky effect, caused by thermal re-radiation of absorbed sunlight, creates systematic orbital drift that operates most efficiently on objects with rotation periods and thermal properties similar to those observed in the debris accompanying 3I Atlas. These non-gravitational forces introduce additional variables into orbital predictions that must be calculated individually for each fragment based on its specific physical characteristics. As the interstellar visitors continue their approach through the outer solar system, The gravitational encounter with Jupiter unfolds with the mathematical inevitability of celestial mechanics operating under the same physical laws that govern planetary motion around our Sun. The perturbations generated by this encounter will determine which fragments achieve sufficient velocity to escape our solar system entirely, which become trapped in elongated heliocentric orbits, and which experience trajectory modifications that lead toward eventual encounters with other planetary masses deeper in our gravitational neighborhood. The gravitational influence extends beyond simple trajectory modification to include rotational dynamics that affect how the fragments respond to solar heating during their continued approach toward perihelion. Jupiter's tidal forces will alter the tumbling rates of irregularly shaped objects, modifying their thermal properties and outgassing patterns in ways that create feedback effects between gravitational perturbations and non-gravitational forces generated by asymmetric sublimation of surface ices. Only needed the universal constancy of gravitational attraction to make these ancient wanderers subject to the same orbital mechanics that shaped our solar system's architecture. Only required the mathematical precision of multi-body gravitational dynamics to predict how contemporary planetary masses will redirect matter that carries chemical signatures from stellar environments that operated 4 billion years ago. Only demanded the kind of computational capability that allows astronomers to calculate gravitational encounters with precision sufficient to determine the ultimate fate of individual ice fragments, revealing that the same inverse square law that drops apples from trees operates with identical mathematical rigor across interplanetary distances, connecting Jupiter's massive presence to the future trajectories of ancient matter through equations that remain constant across cosmic scales and geological time. Microscopic particles liberated from the surface of 3I Atlas and its accompanying debris begin their patient migration toward our Sun, following trajectories governed by the delicate balance between gravitational attraction and radiation pressure forces that operate with mathematical precision across interplanetary distances. These dust grains, ranging in size from nanometers to micrometers, carry within their crystalline structure the same ancient chemistry that characterizes their parent nucleus. Yet their orbital evolution follows dynamics fundamentally different from those governing larger fragments in the debris field. The smallest particles experience radiation pressure forces that exceed solar gravitational attraction, causing them to spiral outward from the comet's nucleus on trajectories that lead toward the heliopause and eventual return to interstellar space. Solar photons transfer momentum to these microscopic fragments through absorption and scattering processes that create accelerations measured in micrometers per second squared, forces barely detectable by terrestrial instruments, yet sufficient to overcome the Sun's gravitational pull on objects with surface area to mass ratios exceeding critical threshold values determined by stellar luminosity and particle density. Intermediate-sized grains follow more complex orbital paths that spiral slowly inward toward our Sun over timescales measured in thousands of years. These particles experience the Poynting-Robertson effect, a relativistic phenomenon where thermal re-radiation of absorbed sunlight creates systematic orbital decay through momentum transfer that operates most efficiently on objects with specific thermal and optical properties. The effect transforms elliptical orbits into gradual spirals that eventually terminate when particles reach temperatures sufficient to vaporize their constituent materials in the intense radiation environment near our Sun's photosphere. Only took absorption and re-emission of stellar photons to create forces capable of altering 4 billion-year-old trajectories. Only needed the finite speed of light to generate momentum transfer effects that systematically modify orbital angular momentum across astronomical distances. Only required the patient accumulation of radiation pressure to guide ancient dust grains through orbital evolution that operates on timescales comparable to the rise and fall of biological species. the gentle irony emerges from physics. These microscopic fragments respond to our sun's radiation with mechanical forces that Isaac Newton could not have anticipated, yet follow trajectories calculable through extensions of classical mechanics that account for the relativistic properties of electromagnetic radiation. Interplanetary dust detection networks monitor the flux of particles entering our solar system's inner regions, distinguishing interstellar contributions from the background population of debris generated by asteroidal collisions and cometary outgassing from solar system objects. The chemical signatures of dust grains originating from 3I Atlas appear in mass spectrometer data as isotopic anomalies that speak of formation in stellar environments where nucleosynthesis operated under conditions different from those that influenced our local stellar neighborhood. These measurements require instruments capable of analyzing individual particles smaller than bacteria while determining their elemental and isotopic compositions with precision sufficient to identify exotic chemical signatures. The orbital mechanics governing dust grain migration create complex spatial distributions that vary with particle size according to the relative importance of gravitational and radiation forces. Computer simulations reveal that grains with radii between 1 and 10 micrometers will populate specific regions of interplanetary space, creating enhanced dust densities along orbital paths that intersect Earth's trajectory around our Sun. These predictions suggest that our planet may encounter measurable increases in interstellar dust influx during the years following 3I Atlas's passage through the inner solar system. Zodiacal light observations detect subtle changes in the brightness and polarization characteristics of sunlight scattered by interplanetary dust, variations that reveal the presence of particles with optical properties distinct from those of typical solar system dust populations. The interstellar grains exhibit scattering behavior that indicates surface compositions enriched in complex organic compounds and exotic silicate minerals that formed under reducing conditions not found in oxidizing planetary environments. These optical signatures provide remote sensing capabilities for monitoring the distribution of ancient matter as it disperses throughout our solar system's inner regions. The mystery deepens with recognition that dust grain survival during 4 billion years of interstellar travel requires protection from cosmic ray bombardment intense enough to alter crystalline structure through radiation damage. Theoretical calculations indicate that maintaining chemical integrity across galactic distances necessitates either extraordinary luck in avoiding high radiation environments or physical shielding mechanisms that current astrophysical models struggle to explain. Yet, the particles arriving from 3I Atlas preserve isotopic signatures that indicate minimal alteration since their formation in molecular cloud environments that no longer exist in our galaxy's current evolutionary phase. Plasma physics models describe the interaction between charged dust grains and the solar wind, the stream of energetic particles flowing outward from our sun's corona at velocities exceeding 400 kilometers per second. Electrostatic forces generated by solar wind bombardment modify grain trajectories through electromagnetic acceleration that operates most efficiently on particles with specific size and composition characteristics. These plasma interactions create additional complexity in orbital predictions that must account for variations in solar wind density and magnetic field strength across the 11-year solar activity cycle. Ground-based meteor radar networks detect the atmospheric entry signatures of interstellar dust grains that complete their orbital spiral by intersecting Earth's atmospheric boundary. The radar echoes reveal particle velocities and trajectory angles that confirm theoretical predictions of Poynting-Robertson orbital decay, providing direct observational verification of relativistic mechanics operating under the weak field conditions that characterize interplanetary space. These measurements require temporal resolution sufficient to track individual meteoric events lasting mere milliseconds, yet carrying kinetic energies comparable to those of rifle bullets. Atmospheric chemistry monitoring reveals the deposition of exotic isotope ratios in stratospheric dust collections. Evidence of interstellar material contributing trace amounts of ancient chemistry to Earth's atmospheric inventory. The deuterium enrichment and unusual nitrogen isotope signatures found in these collections provide terrestrial archives of matter that formed in stellar environments operating under nucleosynthesis conditions that differ from those found in our Sun's nuclear reactions. These atmospheric samples represent the first direct analysis of interstellar matter to reach Earth's surface since the formation of our solar system. As 3i Atlas continues its approach toward perihelion, the liberation of dust grains accelerates according to thermodynamic principles that govern sublimation rates under increasing solar irradiation. Each day of closer approach releases additional populations of microscopic particles that will spend millennia migrating through our solar system's inner regions, carrying chemical messages from galactic epochs when stellar formation operated according to different patterns of element synthesis and distribution, only needed the universal constancy of electromagnetic radiation to subject these ancient particles to forces that Newton's mechanics could not predict. Yet Einstein's relativistic corrections describe with mathematical precision only required the patient interaction between stellar photons and microscopic matter to guide 4-billion-year-old dust grains through orbital evolution that operates on timescales longer than human civilization. Only demanded the kind of physical precision that makes radiation pressure measurable across astronomical distances, revealing that even the momentum carried by individual photons accumulates into forces sufficient to alter the fate of matter that preserves chemical archives from stellar environments we can model but never directly observe. Connecting these wandering particles to the fundamental properties of light itself through equations that remain constant across cosmic distances and geological time. Deep space monitoring stations scattered across Earth's surface turn their sensitive receivers toward the approaching interstellar visitors, detecting electromagnetic signatures that emerge from within the debris field with characteristics unlike any phenomena observed in objects native to our solar system. The radio telescopes, with their aluminum dishes spanning hundreds of meters, gather signals that speak of plasma interactions, magnetic field disturbances, and charged particle dynamics operating under conditions that bridge the gap between interstellar space and our Sun's gravitational domain. The Very Large Array in New Mexico coordinates with facilities in Australia, Chile, and the Canary Islands to create a virtual aperture spanning continental distances, achieving angular resolution sufficient to distinguish electromagnetic sources separated by mere kilometers within the debris field. These interferometric observations reveal that radio emissions originate not from the primary nucleus of 3i Atlas, but from smaller companions distributed throughout the gravitational swarm, suggesting that electromagnetic phenomena accompany the sublimation processes occurring across multiple fragments simultaneously. Spectral analysis of the radio signals reveals emission lines corresponding to molecular transitions in hydroxyl radicals, water vapor, and complex organic species. Yet the signal characteristics display anomalies that challenge current understanding of how cometary atmospheres interact with electromagnetic radiation. The emission frequencies show systematic shifts that indicate plasma densities exceeding those predicted by standard models of cometary coma formation, suggesting that the ancient ice matrices respond to solar heating through mechanisms that differ from processes observed in solar system comets. Only took electromagnetic radiation traveling at light speed to carry information about plasma physics operating millions of kilometers from Earth. Only needed radio waves with frequencies precise enough to reveal molecular energy level transitions in environments where particle densities approach those of interstellar space. Only required the patient accumulation of signal data to detect phenomena that operate according to the same electromagnetic principles across interplanetary distances as they do in terrestrial plasma physics laboratories. The quiet irony settles like radiostatic. These ancient visitors generate electromagnetic signatures readable by human technology. Yet, the physical processes creating these signals operate under conditions that have never been directly studied in any laboratory environment. Deep space communication networks detect modulated signals within the radio emissions that correlate with the rotation periods of individual fragments in the debris field. The signal variations follow patterns that suggest electromagnetic coupling between the rotating objects and their surrounding plasma environments, creating conditions analogous to those found in pulsar magnetospheres, but operating under the vastly different conditions that characterize weakly ionized cometary atmospheres. These observations require timing precision sufficient to detect signal variations on timescales of minutes across transmission delays measured in hours. The electromagnetic phenomena appear most prominently at frequencies corresponding to cyclotron resonance in the local magnetic field environment, indicating that charged particles in the cometary atmospheres follow helical trajectories around magnetic field lines embedded in the solar wind. Computer simulations suggest that these plasma dynamics generate coherent radio emission through mechanisms similar to those responsible for auroral radio phenomena in planetary magnetospheres, yet operating under magnetic field conditions orders of magnitude weaker than those found near any planet in our solar system. Radiopolarimetry reveals that the electromagnetic emissions carry information about magnetic field orientations within the debris field, providing remote sensing capabilities for phenomena that remain invisible to optical observations. The polarization characteristics indicate that individual fragments possess weak intrinsic magnetic fields, possibly preserved from the original molecular cloud environment, where this matter first condensed under conditions where magnetic field strength exceeded current interstellar medium values by factors that speak of stellar formation processes operating under different galactic conditions. The mystery deepens with recognition that maintaining coherent electromagnetic emission across the debris field requires plasma densities that exceed those expected from simple sublimation of water ice and other volatile compounds. Theoretical calculations indicate that the observed radioluminosity demands ionization rates that could result only from enhanced cosmic ray bombardment or exposure to energetic particle populations not found in the current interplanetary environment. Yet, the electromagnetic signatures persist with intensities that suggest ongoing particle acceleration through mechanisms that current plasma physics models struggle to explain. Radio astronomy networks detect burst-like emission events that occur with statistical regularity, yet show no obvious correlation with fragment rotation periods or solar wind conditions. These transient signals last for seconds to minutes, displaying frequency drift patterns that indicate particle acceleration through magnetic reconnection events or shockwave formation in the tenuous plasma environments surrounding individual debris fragments. The burst characteristics resemble those observed in stellar radio emission, yet operate under density and temperature conditions that differ by orders of magnitude from those found in stellar coronae. Electromagnetic modeling reveals that the radio emissions require plasma temperatures exceeding those achievable through simple photoionization by solar ultraviolet radiation, suggesting that additional heating mechanisms operate within the cometary atmospheres. The energy balance calculations indicate that magnetic field dissipation, turbulent heating, or wave-particle interactions may contribute thermal energy to the plasma environments surrounding the debris fragments, creating conditions where electromagnetic instabilities can generate the observed radio phenomena. Deep space interferometry detects systematic variations in radio source positions that correlate with gravitational perturbations from Jupiter's approaching influence, revealing that electromagnetic emission regions move with the debris fragments as their trajectories respond to planetary gravitational fields. These positional measurements achieve accuracy sufficient to track electromagnetic sources across distances comparable to planetary orbital radii, providing direct observational evidence that radio emission regions remain gravitationally bound to their parent fragments despite the turbulent plasma conditions that characterize cometary atmospheres. Very long baseline interferometry observations reveal fine structure within the radio emission regions that indicates multiple source components distributed around individual fragments according to the geometry of magnetic field lines and plasma flow patterns. The spatial resolution achieved through continental scale baseline separations shows that electromagnetic phenomena extend across regions comparable in size to terrestrial mountain ranges, yet operate under physical conditions where particle collision rates approach those found in the best laboratory vacuum chambers. As the interstellar visitors continue their approach through our solar system's outer regions, radio observatories maintain continuous surveillance of electromagnetic phenomena that provide unique insights into plasma physics operating under conditions that bridge interstellar and interplanetary environments. The signal characteristics evolve with mathematical predictability as solar wind density and magnetic field strength increase with proximity to our Sun. Yet the underlying emission mechanisms display complexities that challenge current understanding of how ancient matter responds to contemporary electromagnetic environments. The radio emissions emerging from the debris field represent more than curious electromagnetic phenomena. They constitute direct observations of plasma physics operating on matter that carries magnetic field signatures from galactic environments that operated under conditions different from those found in our current stellar neighborhood. Only needed the universal constancy of electromagnetic radiation to make these ancient plasma interactions detectable by terrestrial radio telescopes. Only required the patient accumulation of signal data to reveal electromagnetic processes that operate according to the same physical principles across interplanetary distances as they do in laboratory plasma physics experiments. Only demanded the kind of instrumental sensitivity that allows radio astronomers to detect plasma dynamics in environments where particle densities barely exceed those of interstellar space, revealing that electromagnetic phenomena accompanying these ancient visitors follow the same fundamental laws that govern all interactions between charged particles and magnetic fields. Connecting radio emissions from 4 billion-year-old matter to the mathematical framework of classical electrodynamics through equations that remain valid across cosmic distances and geological time. The stream of charged particles flowing outward from our Sun's corona encounters the tenuous atmospheres of 3I Atlas and its debris companions, creating pressure waves that propagate through the solar plasma with characteristics unlike any phenomena observed during interactions with objects native to our solar system. Solar wind velocities exceeding 400 kilometers per second generate bow shock formations around the larger fragments, compressing the interplanetary magnetic field into regions where plasma dynamics operate under conditions that bridge the gap between stellar wind physics and cometary atmospheric science. Magnetohydrodynamic modeling reveals that the solar wind interaction creates standing wave patterns in the plasma environment surrounding each fragment, generating compression and rarefaction zones that modulate the electromagnetic properties of interplanetary space across distances comparable to planetary orbital radii. These pressure variations propagate at the Alph-Venn velocity, the characteristic speed of magnetic disturbances in ionized gases, creating signal transmission delays that allow ground-based instruments to monitor the real-time evolution of plasma dynamics occurring millions of kilometers from Earth. The chemical composition of gases sublimating from the ancient ice matrices influences solar wind interaction dynamics through ionization processes that create plasma populations with mass and charge characteristics distinct from those found in typical interplanetary environments. Deuterium-enriched water vapor, exotic organic compounds, and isotopically anomalous carbon dioxide generate ion species that respond to electromagnetic fields according to their specific mass-to-charge ratios, creating plasma dynamics that differ measurably from those observed during solar-wind interactions with solar system comets. Only took electromagnetic forces operating at light speed to couple 4-billion-year-old matter with contemporary stellar plasma. Only needed charged particle interactions to create pressure waves that propagate across astronomical distances according to the same magnetohydrodynamic principles that govern stellar wind dynamics. Only required the universal constancy of electromagnetic fields to make ancient chemistry responsive to our Sun's particle outflow through forces that operate with identical mathematical precision across interplanetary space. The cosmic irony emerges gently. These interstellar visitors respond to our Sun's influence through plasma physics that Isaac Newton could not have anticipated, yet follow electromagnetic laws that James Clerk Maxwell formulated in terrestrial laboratories. Spacecraft instrumentation throughout the outer solar system detects the passage of pressure waves generated by solar wind interactions with the debris field, revealing propagation characteristics that provide remote sensing capabilities for plasma phenomena occurring beyond direct observational range. The Voyager probes, now operating in the outer heliosphere, register magnetic field perturbations that originated from encounters between solar wind plasma and the ancient matter accompanying 3I Atlas, demonstrating that electromagnetic disturbances from these interactions propagate across the entire span of our solar system's gravitational domain. The plasma dynamics create acceleration regions where charged particles gain kinetic energy through electromagnetic field interactions, generating energetic particle populations that contribute to the radio emission phenomena detected by terrestrial observatories. Magnetic reconnection events, caused by the interaction between solar wind magnetic fields and intrinsic field structures preserved within the debris fragments, create localized acceleration zones where particle energies approach those found in planetary radiation belts despite operating under magnetic field conditions orders of magnitude weaker. Solar wind composition monitoring reveals that the passage of 3I Atlas and its companions creates measurable perturbations in the chemical properties of interplanetary plasma, introducing trace amounts of isotopically exotic material into the solar particle stream. Mass spectrometers aboard deep space missions detect deuterium enrichment, unusual nitrogen isotope ratios, and organic molecular fragments that speak of chemical processing in stellar environments operating under nucleosynthesis conditions different from those found in our Sun's nuclear reactions. The mystery deepens with observations that solar wind interaction efficiency varies significantly among different fragments in the debris field, suggesting that plasma coupling depends on surface properties that were established during formation processes in the original molecular cloud environment. Computer simulations indicate that electromagnetic interaction strength correlates with magnetic field orientations preserved from the interstellar medium. Yet current models cannot explain how such field structures could survive 4 billion years of cosmic ray bombardment and gravitational encounters with multiple stellar systems. Plasma wave observations detect low-frequency electromagnetic oscillations generated by the interaction between solar wind flow and the irregular mass distribution within the debris field, creating resonance phenomena analogous to those found in planetary magnetospheres, but operating under vastly different density and magnetic field conditions. These waves propagate through the solar plasma with frequencies that correspond to ion cyclotron motion in the local magnetic field environment, generating electromagnetic signatures detectable by radio telescopes across interplanetary distances. The solar-wind interaction creates wake regions behind each fragment where plasma flow velocity decreases and particle density increases, forming elongated structures that extend downstream for distances measured in millions of kilometers. These plasma tails follow trajectories that reveal the three-dimensional structure of solar wind flow patterns around irregularly shaped objects, providing observational data for testing magnetohydrodynamic models of stellar wind interactions with small bodies under conditions that cannot be reproduced in terrestrial laboratory environments. Heliospheric monitoring networks track the propagation of pressure waves generated by solar wind encounters with the debris field, revealing that electromagnetic disturbances travel outward through the solar plasma with velocities that depend on local magnetic field strength and particle density according to magnetohydrodynamic theory. These observations provide direct measurements of plasma parameters throughout the outer solar system, using the ancient visitors as natural probes for investigating electromagnetic phenomena under conditions that span the transition from interplanetary to interstellar space. Particle acceleration modeling reveals that solar wind interactions with the debris field create conditions suitable for generating high-energy cosmic ray populations through mechanisms similar to those operating in supernova remnants and stellar wind collision zones. The electromagnetic field configurations generated by plasma flow around irregular objects, provide acceleration regions where charged particles can gain energy sufficient to contribute to the galactic cosmic ray background, suggesting that interactions between stellar winds and interstellar matter may represent a previously unrecognized source of energetic particle production. As 3I Atlas and its companions continue their approach toward our Sun, the intensity of solar wind interactions increases according to the inverse square law that governs stellar radiation and particle flux, creating plasma conditions that will approach those found in the inner solar system, where electromagnetic phenomena operate under magnetic field and particle density conditions that differ dramatically from the interstellar environment where this matter spent 4 billion years in frozen isolation. The solar wind interactions accompanying these ancient visitors represent more than curious plasma physics phenomena. They constitute direct observations of electromagnetic processes that connect contemporary stellar activity with matter that preserves chemical and magnetic field signatures from galactic environments operating under conditions different from those found in our current stellar neighborhood. Only needed the universal constancy of electromagnetic forces to make 4 billion-year-old matter responsive to our Sun's particle outflow through plasma dynamics that operate according to the same physical principles across interplanetary distances. Only required the mathematical framework of magnetohydrodynamics to describe pressure wave propagation through ionized gases that carry isotopic signatures from stellar nucleosynthesis processes we can model but never directly observe. Only demanded the kind of instrumental precision that allows spacecraft throughout our solar system to detect electromagnetic disturbances generated by the interaction between ancient chemistry and contemporary stellar plasma, revealing that the same electromagnetic laws that govern terrestrial plasma physics operate with identical mathematical rigor across cosmic distances, connecting these interstellar visitors to our Sun's influence through forces that Maxwell's equations describe with precision that remains constant across galactic distances and geological time. Orbital mechanics calculations reveal with mathematical certainty that 3I Atlas follows a hyperbolic trajectory that will carry this ancient wanderer beyond our Sun's gravitational influence, never to return to the stellar neighborhood that has become its temporary home. The comet's orbital eccentricity of 1.93 describes a path that intersects our solar system for mere months before continuing an eternal journey through galactic space, carrying with it the chemical signatures of stellar formation processes from epochs when the Milky Way itself operated according to different patterns of element synthesis and distribution. Computer simulations trace the visitor's future trajectory across galactic coordinates, revealing that its departure velocity will exceed the escape speed necessary to overcome our Sun's gravitational attraction by margins that ensure permanent separation from our stellar system. The calculations require accounting for gravitational perturbations from all major planetary masses, relativistic corrections to Newtonian mechanics, and the subtle influence of solar radiation pressure on the comet's irregular nucleus. Yet, the mathematical precision of celestial mechanics allows astronomers to predict the wanderer's position with accuracy measured in kilometers across distances that will eventually span parsecs. The departure trajectory carries 3I Atlas toward the constellation Telescopium, where it will spend approximately 67,000 years crossing the gravitational boundary that separates our solar system from the interstellar medium. During this extended exit phase, the comet will gradually cool as solar radiation intensity decreases according to the inverse square law, causing sublimation processes to cease and returning the nucleus to the frozen silence that characterized its 4 billion-year journey through galactic space before encountering our Sun's gravitational field. Only took a few months of solar system passage to complete an orbital arc that spans half the galaxy's circumference. Only needed gravitational focusing by our Sun to compress billions of years of interstellar wandering into a mathematically predictable trajectory that terminates in eternal darkness. Only required the universal constancy of celestial mechanics to ensure that this visitor's departure follows the same physical laws that govern planetary motion around stars throughout the observable universe. The profound irony settles like orbital mathematics. This ancient chemistry will spend more time departing our solar system than it spent approaching, following hyperbolic geometry that Isaac Newton could calculate yet never directly observe across the astronomical distances involved. Astrometric observations reveal that the comet's trajectory, when extended beyond our solar system's gravitational boundary, will carry it through regions of interstellar space where stellar density differs from that found in our current galactic neighborhood. The mathematics of galactic dynamics predict that 3I Atlas will encounter gravitational perturbations from distant star systems during the next several million years. Yet none of these interactions will possess sufficient magnitude to alter its trajectory enough to bring the wanderer back toward our Sun or any other stellar system it has previously visited. The departure process will reverse the awakening that characterized the comet's approach, as decreasing solar radiation allows surface temperatures to drop toward the 2.7 Kelvin background of cosmic microwave radiation. Sublimation processes will gradually cease as thermal energy input falls below the threshold necessary to maintain phase transitions in the ancient ice matrices, causing the tenuous atmosphere that made the comet observable to dissipate into the solar wind until only the dark nucleus remains visible to the most sensitive telescopes. Long-term orbital integration reveals that 3I Atlas will require approximately 4 million years to reach the distance where our Sun's gravitational influence becomes negligible compared to that of neighboring stars in the local stellar association. During this extended departure phase, the comet will serve as a gravitational probe for measuring the mass distribution of objects in our solar system's outer regions, as minute trajectory perturbations reveal the presence of undiscovered trans-Neptunian objects through their gravitational signatures. The mystery embedded in the comet's departure lies in the recognition that its future trajectory will carry chemical samples of our solar system's interplanetary environment back into galactic space, reversing the process that brought ancient stellar chemistry into our gravitational neighborhood. Dust particles and trace gases acquired during passage through our heliosphere will accompany the departing visitor, creating a chemical exchange between our solar system and the interstellar medium that operates on timescales measured in millions of years. Gravitational mechanics calculations reveal that some debris fragments will achieve escape velocities that exceed those of the primary nucleus, causing portions of the ancient debris field to depart our solar system ahead of their gravitational parent. These fragments will follow independent trajectories through interstellar space, carrying identical chemical signatures to different regions of the galaxy where they may eventually encounter other stellar systems during the hundreds of millions of years required for galactic orbital motion to bring them within gravitational range of distant stars. Deep space tracking networks will maintain surveillance of the departing visitor for decades after its closest approach to our Sun, monitoring the gradual fade in brightness and spectroscopic activity as thermal processes shut down according to thermodynamic principles that operate with mathematical precision across astronomical distances. These observations will provide the last direct measurements of matter that preserves chemical archives from stellar formation epochs that no longer exist in our galaxy's current evolutionary phase. The departure trajectory calculations must account for the gradual decrease in the comet's mass as sublimation processes remove material from the nucleus during the months surrounding perihelion passage. This mass loss creates reactive forces that slightly modify the orbital path through mechanisms analogous to rocket propulsion, yet operating through natural thermodynamic processes that follow the same physical principles, whether they occur in spacecraft engines or ancient ice matrices responding to stellar radiation. Radio telescopes will continue detecting electromagnetic signatures from the departing debris field until solar-wind interactions become too weak to maintain the plasma conditions necessary for coherent radio emission. These final observations will provide unique data about plasma physics operating under conditions that transition gradually from interplanetary to interstellar environments, bridging the gap between stellar wind dynamics and the electromagnetic phenomena that characterize the diffuse interstellar medium. As 3I Atlas begins its departure from our solar system's inner regions, the mathematical certainty of its hyperbolic trajectory provides both poetic and scientific closure to a gravitational encounter that has lasted mere months, yet revealed chemical information spanning billions of years of galactic evolution. The orbital mechanics ensure that this ancient wanderer will continue its journey through interstellar space with the same patient inevitability that guided its 4 billion-year approach. Carrying chemical messages from stellar formation epochs, we can model but never directly observe into galactic regions our species will never visit. The departure represents more than the end of a brief gravitational encounter. It constitutes the return of ancient matter to the cosmic environment where it will spend eternity. Enriched by trace additions of contemporary solar system chemistry, yet preserving the fundamental isotopic and molecular signatures that speak of stellar nucleosynthesis from galactic epochs when our galaxy followed different patterns of star formation and element distribution, only needed the mathematical precision of orbital mechanics to ensure that this visitor's departure follows hyperbolic geometry that remains constant across cosmic distances. Only required the universal constancy of gravitational attraction to make this ancient wanderer subject to the same celestial mechanics that govern all orbital motion around stars throughout the observable universe. Only demanded the kind of astronomical patience that allows 4 billion-year-old chemistry to complete its brief intersection with our solar system according to mathematical principles that Newton formulated yet could never observe operating across the interstellar distances where this visitor will spend eternity, revealing that departure follows the same physical laws as approach, connecting this temporary gravitational encounter to the eternal patterns of celestial motion that guide all matter through the cosmic dance of gravity, time, and space. The chemical composition of 3I Atlas provides a comparative lens through which astronomers examine the fundamental differences between stellar formation processes that operated in ancient galactic environments and those that characterize contemporary star-forming regions throughout our current stellar neighborhood. Each isotopic ratio and molecular abundance detected in the comet's sublimating atmosphere represents a data point in the vast experiment of galactic chemical evolution, offering insights into nucleosynthesis pathways that operated under physical conditions no longer found in the Milky Way's present evolutionary phase. Spectroscopic analysis reveals deuterium to hydrogen ratios that exceed solar system values by factors indicating formation in molecular cloud environments where stellar winds and supernova shock waves created different patterns of isotopic enrichment than those found in our local stellar association. The heavy hydrogen abundance speaks of stellar populations whose mass distributions favored the production of deuterium through nuclear processes that operated in stellar cores, with different temperature and pressure profiles than those found in stars currently forming in nearby spiral arms. Comparative planetology studies examine how the exotic chemistry preserved in 3I Atlas's nucleus differs from that found in objects formed within our solar system's protoplanetary disk. The nitrogen isotope ratios indicate synthesis in stellar environments where neutron capture processes operated under conditions that produced different isotopic signatures than those found in Earth's atmosphere, meteoritic samples, or any other solar system reservoir. These measurements provide direct evidence that stellar nucleosynthesis followed different pathways in the galactic environments where this ancient wanderer first condensed from cosmic gas and dust. Only took 4 billion years of preservation in interstellar space to maintain chemical signatures that reveal stellar formation processes from galactic epochs we can model but never directly observe. Only needed temperatures approaching absolute zero to prevent thermal equilibration that would erase isotopic fingerprints from extinct stellar environments. Only required the patient accumulation of spectroscopic data to decode chemical messages written in molecular transitions that preserve information about nuclear reactions in stellar cores that operated under different galactic conditions. The scientific irony emerges quietly. This comparative analysis reveals that our solar system represents just one example of stellar formation chemistry, while interstellar visitors like 3I Atlas carry samples of the broader galactic experiment in element synthesis and distribution. Carbon isotope ratios in complex organic molecules emerging from the comet's nucleus indicate formation through surface chemistry processes that operated on grained surfaces exposed to cosmic ray fluxes and ultraviolet radiation fields different from those found in our current interstellar neighborhood. The carbon-13 enhancement suggests that stellar winds from asymptotic giant branch stars contributed material to the molecular cloud environment through mass loss processes that operated under different stellar evolution timescales than those characterizing current stellar populations in our galactic region. Sulfur chemistry preserved in the ancient ice matrices reveals nucleosynthesis signatures that speak of stellar formation regions where massive star evolution followed different patterns than those observed in contemporary star-forming complexes. The sulfur isotope ratios indicate synthesis in stellar cores, where neutron flux densities and temperature profiles created different reaction pathways for producing heavy sulfur isotopes through nuclear processes that operated under the extreme conditions found in pre-supernova stellar evolution phases. The mystery deepens with recognition that comparative analysis of 3I Atlas chemistry reveals systematic differences from solar system composition that extend beyond simple isotopic variations to include fundamental differences in the relative abundances of different chemical species. Computer models of molecular cloud chemistry indicate that the observed composition requires formation under physical conditions where stellar radiation fields, cosmic ray intensities, and magnetic field strengths all differed measurably from those found in our current galactic environment. Oxygen isotope systematics in water vapor, sublimating from the comet's nucleus, provide constraints on the stellar sources that contributed material to the original molecular cloud through supernova nucleosynthesis and stellar wind mass loss processes. The oxygen-17 and oxygen-18 abundances indicate mixing between materials produced in different stellar mass ranges, suggesting that the stellar formation region experienced chemical enrichment from both massive stars that ended as supernovae and intermediate mass stars that contributed material through asymptotic giant branch winds. Comparative studies of organic chemistry preserved in 3I Atlas reveal molecular complexity that challenges current understanding of how carbon-based compounds form and survive in the interstellar medium. The detection of polycyclic aromatic hydrocarbons and other complex organics indicates that carbon chemistry operated more efficiently in the comet's formation environment than models predict for typical interstellar conditions, suggesting that stellar formation regions 4 billion years ago provided enhanced opportunities for organic molecule synthesis and preservation. Laboratory analysis of terrestrial samples provides reference standards for interpreting the exotic chemistry observed in interstellar visitors. Yet, the comparison reveals that Earth's geochemical evolution followed pathways that differ systematically from those preserved in ancient cometary nuclei. The isotopic signatures found in terrestrial rocks, atmospheric gases, and biological materials all reflect processing through planetary formation and geological evolution processes that altered the original stellar chemistry inherited from our solar system's molecular cloud environment. Meteoritic chemistry offers additional comparative data for understanding how different stellar formation environments produce systematic variations in isotopic compositions and elemental abundances. Primitive meteorites preserve some signatures of early solar system chemistry. Yet even these ancient samples show evidence of thermal and chemical processing that modified their original compositions in ways that make direct comparison with interstellar chemistry challenging to interpret without sophisticated models of planetary accretion and differentiation processes. The comparative analysis extends beyond simple chemical measurements to include examination of physical properties that reveal details about the mechanical and thermal conditions that operated during stellar formation in different galactic environments. The crystalline structure of water ice, preserved in 3I Atlas, indicates formation under specific temperature and pressure conditions that differ from those expected in typical molecular cloud environments, suggesting that stellar formation processes 4 billion years ago operated under different physical parameters than those characterizing contemporary star-forming regions. As 3I Atlas continues its journey through our solar system, the comparative planetology analysis accumulates into a chemical portrait of galactic evolution that spans billions of years of stellar death and birth. The molecular signatures emerging from this ancient nucleus provide direct sampling of stellar formation chemistry from epochs when the galaxy operated according to different patterns of nucleosynthesis and element distribution, offering insights into cosmic chemical evolution that remain inaccessible through any other observational approach. The comparative perspective reveals that our solar system represents one specific example of stellar formation chemistry, while the broader galaxy has experimented with different approaches to element synthesis and molecular assembly across billions of years of stellar evolution. Only needed the preservation of ancient chemistry in interstellar wanderers to provide direct samples of galactic chemical evolution from epochs our species can model but never directly observe. Only required the universal constancy of atomic physics to make isotopic signatures readable across billions of years of cosmic time. Only demanded the kind of comparative analysis that allows scientists to place our solar system's chemistry in the context of galactic evolution, revealing that stellar formation has followed different pathways throughout cosmic history, connecting our local stellar environment to the broader patterns of nucleosynthesis and chemical distribution that characterize the galaxy's ongoing experiment in creating the elements that make planets, atmospheres, and ultimately the complex chemistry that enables life to emerge from stellar death and birth across cosmic distances and geological time. Observatories scattered across Earth's continents coordinate their efforts with the precision of a global scientific orchestra, each facility contributing specialized capabilities to the comprehensive surveillance of 3I Atlas as the ancient visitor approaches the fading threshold of observational detectability. The Atacama Large Millimeter Array in Chile points its aluminum receivers toward wavelengths that reveal molecular transitions in the comet's tenuous atmosphere, while radio telescopes in Australia and the Canary Islands monitor electromagnetic phenomena that speak of plasma dynamics operating under conditions that bridge interstellar and interplanetary space. The European Southern Observatory's Very Large Telescope Array employs adaptive optics systems that compensate for atmospheric turbulence with mirror adjustments measured in nanometers, achieving resolution sufficient to distinguish surface features on the comet's nucleus across distances spanning millions of kilometers. These observations require exposure times extending through entire nights, accumulating photons that traveled across the solar system to carry spectroscopic information about chemistry that preserves signatures from stellar formation epochs predating our sun's ignition of nuclear fusion. Infrared observatories operating above Earth's atmospheric water vapor utilize space-based platforms to monitor thermal emission from dust grains liberated from the comet's surface, detecting temperature variations that reveal details about sublimation processes operating on ancient ice matrices exposed to solar radiation for the first time in 4 billion years. The thermal signatures require instruments sensitive enough to distinguish temperature differences measured in fractions of Kelvin across astronomical distances, where solar heating barely exceeds the background warmth of cosmic microwave radiation. Only took the coordinated efforts of dozens of observatories to gather comprehensive data about chemistry that formed before Earth's accretion from planetary debris. Only needed international cooperation spanning continents to monitor phenomena that operate according to physics principles constant across galactic distances, yet never before observed under the specific conditions that characterize interstellar objects responding to contemporary solar radiation. Only required the patient accumulation of observational data to decode molecular messages preserved in frozen archives that wandered through galactic space until gravitational choreography guided them within range of terrestrial instruments. The scientific irony settles like global coordination. This ancient visitor demands the most sophisticated observational capabilities humanity has developed, yet carries chemistry that operated under physical conditions simpler than those found in any terrestrial laboratory. Ground-based spectrometers operating across wavelength ranges from radio frequencies to gamma rays coordinate their observations to create comprehensive chemical inventories of gases sublimating from the comet's nucleus and accompanying debris field. Each facility contributes specialized measurements that reveal different aspects of the complex chemistry emerging as ancient ices respond to increasing solar heating through thermodynamic processes that follow universal physical laws, yet operate under environmental conditions that exist nowhere else in our contemporary solar system. The coordination extends beyond individual observatories to include space-based missions throughout our solar system, from spacecraft monitoring solar wind conditions near Earth to the Voyager probes detecting electromagnetic disturbances in the outer heliosphere generated by plasma interactions with the ancient debris field. This distributed network of instruments provides three-dimensional mapping of phenomena that span distances comparable to planetary orbital radii, yet operate through electromagnetic processes that propagate at light speed across interplanetary space. Deep space tracking networks maintain continuous surveillance of the comet's trajectory with positional accuracy sufficient to detect gravitational perturbations caused by undiscovered objects in our solar system's outer regions. The measurements require atomic clock synchronization between facilities separated by continental distances, creating timing precision that allows astronomers to monitor orbital evolution in real time as the visitor responds to gravitational influences from planetary masses and the subtle effects of solar radiation pressure on its irregular nucleus. The mystery embedded in this global observational campaign lies in the recognition that modern astronomical capabilities allow detailed study of matter that preserves chemistry from galactic epochs when stellar formation operated under fundamentally different conditions than those found in our current stellar neighborhood. Computer networks process data streams flowing from observatories worldwide, applying analysis techniques that reveal isotopic signatures and molecular abundances. Speaking of nucleosynthesis processes that operated in stellar cores, whose fusion reactions followed pathways no longer active in the galaxy's present evolutionary phase, adaptive optic systems compensate for atmospheric disturbances with feedback loops that operate faster than human reflexes, maintaining optical clarity sufficient to resolve details on objects millions of kilometers distant yet smaller than terrestrial mountains. These technologies allow ground-based telescopes to achieve resolution rivaling that of space-based platforms, democratizing access to observational capabilities that make ancient interstellar chemistry readable through instruments that operate according to the same optical principles, whether examining distant galaxies or nearby cometary nuclei. International cooperation protocols ensure that observational data flows freely between facilities despite political boundaries, creating a global scientific commons dedicated to understanding chemistry that carries information about stellar formation processes from epochs when the galaxy itself operated according to different patterns of element synthesis and distribution. The coordination requires real-time communication between time zones, languages, and scientific cultures, yet achieves precision sufficient to track phenomena that operate according to mathematical principles constant across cosmic distances. Robotic telescope networks respond automatically to changes in the comet's brightness and spectroscopic characteristics, adjusting observation schedules and instrumental configurations according to algorithms that optimize data collection efficiency across multiple wavelength ranges simultaneously. These automated systems maintain surveillance capabilities that exceed human attention spans, monitoring phenomena that evolve on timescales ranging from minutes to months, while accumulating data with statistical precision that reveals subtle chemical signatures embedded in noise levels that would mask important scientific information. The global observational network represents more than a collection of individual telescopes. It constitutes a distributed scientific instrument capable of monitoring interstellar chemistry across wavelength ranges that span the entire electromagnetic spectrum. Each facility contributes specialized capabilities that complement measurements made by others, creating observational synergies that reveal details about ancient matter that remain invisible to any single instrument or technique. As 3i Atlas continues its approach toward the observational limits imposed by its increasing distance from Earth, the coordinated surveillance campaign accumulates into a comprehensive scientific archive documenting the first detailed study of interstellar chemistry preserved in a visitor from galactic space. The data flowing from observatories worldwide will require years of analysis to fully decode, yet already reveals chemical signatures that speak of stellar formation processes operating under conditions that differ measurably from those found in our solar system's formation environment. The coordination of ground-based telescope networks represents humanity's most sophisticated attempt to study matter that carries chemical archives from stellar environments we can model but never directly observe. Only needed the development of global communication networks to coordinate observations across continental distances with timing precision measured in microseconds. Only required the standardization of data formats and analysis protocols to enable scientific cooperation that transcends political and cultural boundaries. Only demanded the kind of international scientific collaboration that allows dozens of observatories to function as components of a single distributed instrument, revealing that the ancient chemistry preserved in this interstellar visitor can be decoded only through observational capabilities that represent the collective scientific achievements of human civilization. Connecting ground-based telescopes across Earth's surface through coordination protocols that operate with the same precision as the celestial mechanics that guide this wanderer through our solar system, according to gravitational laws that remain constant across galactic distances and geological time. some particles liberated from the ancient surface of 3I Atlas, and its accompanying debris will remain gravitationally bound to our solar system long after the primary nucleus departs for interstellar space, following elongated orbital paths that will carry these fragments of 4-billion-year-old chemistry through our planetary neighborhood for millions of years to come. The smallest dust grains, subjected to radiation pressure forces that overcome solar gravitational attraction, will spiral outward toward the heliopause and eventual return to galactic space. Yet intermediate-sized particles will achieve orbital velocities that place them in permanent residence within our Sun's gravitational domain. Orbital mechanics calculations reveal that fragments with specific size and density characteristics will follow elliptical paths that bring them periodically within range of terrestrial instruments, creating opportunities for ongoing study of interstellar chemistry long after the parent comet has faded beyond observational reach. These captured objects